uh, to all. Very good evening and good morning to everyone who are present over here. On behalf of IIT Guwahati SP Student Chapter, I warmly welcome you all today's session under this Alpha Technical Series. Artificial lift evolution from basics to unconventional is today our topic. We are delighted to have with us students, research scholars, and also faculty members and industrial professions joining from across the country for this insightful session. So today's session is a part of Alpha series, an initiative which is made focusing on the advanced technical understanding in production engineering, multi-phase flow, and data-driven optimization. Through this series, we aim to bring together industry experts and academics to provide practical insights into real world production challenge, emerging technologies, and modern engineering solutions into the energy sector. So, it's my great pleasure to introduce our distinguished speaker for today's session. We are honored to have Dr. Rajan Chokshi, optimizer at Accutant Solution, and a as former SP distinguished lecturer. Dr. Chokshi brings over 3 decades of global experience in artificial lift system, multi-phase flow, real-time production optimization, and digital oilfield technologies. His work lies at the intersection of production engineering, advanced analytics, and real-world field optimization, making today's session extremely valuable for us. With this, I would like to invite Dr. Rajan Chokshi to deliver this talk. Sir, we are honored to have have you with us today. The stage is yours, sir. You can start.
Thank you so much. And it's my pleasure and an honor to have been invited to give this talk. Now, this talk is a combination of multiple talks that I have given. Actually, it is a part of my, almost a semester long curriculum that I have taught in the graduate schools here in the United States, and also part of my two separate distinguished lecture series. So this is a very high level outline. And the last part, the future trends in artificial lift analytics, it is more, I have left it for you guys to ask me questions rather than me telling you about it. I have a whole 1 day class on that, data sciences and analytics. And if there's an interest, we can organize that. So I'll briefly introduce yourself, and it was very helpful what you talked about the program because I was not aware of it. So I think there'll be some similarities that you'll find in my background and what you guys are trying to accomplish. Um, so we'll talk about artificial lift introductions. Even though you mentioned that you have learned something, so I'll go over that part very fast. And then I'll talk a little bit about selection application, followed by what is different in unconventional and tight oil applications. And I'll take one basin, Permian Basin, which is the largest producer. Uh, I think if it was a country by itself, it would be number four or number three, depending upon how you look at it. We'll talk briefly at the role of digital oil field, which is the underpinning of the analytics side of it, right? So again, you have already given some nice introduction, and thanks for that. And this tells you about some of my experience. There is a barcode here on the bottom right that tells you how to connect with me. Um, so my journey in the petroleum engineering started with the LD College of Engineering, Gujarat University. Just like you guys, I was also a chemical engineer in my undergrad in 1982. Then I went to IIT Kanpur. That's where I did my master's, and that's where I picked up some programming skills as well as industrial engineering practices as a part of my master's. And then I went to work for ONGC in Institute of Oil and Gas Production Technology. I was there until about 89 December or so. And fast forward from there, I went to University of Tulsa. If any of you have a good idea about going for further studies, then I cannot recommend it highly enough. So that's where I did my PhD in petroleum engineering. Now, before that, both the degrees were in chemical. So all the knowledge that I acquired before I came to Tulsa was through on-the-job training at the ONGC, and I cannot be thankful enough for my boss, late Dr. Ramashish Rai, for that. After finishing my PhD, I started working with my advisor, Dr. Zalmer Schmidt's company, which was also co-founded by Dr. Kermit Brown, if you guys know about any. And I was in Tulsa, Oklahoma until about 2004. And believe it or not, during that period, I also managed to work at United Parcel Service, UPS, the package delivery company. And that's where I picked up some of the enterprise application programming experience. And my project management experience that I acquired while I was working in the oil industry was very helpful in managing team of developers, researchers, etc. And then I moved to Houston, which is, as you all know, probably energy capital of the world. And I've been there since 2006 or so, so almost 20 years. So this is my journey over the course of about 40 plus years. One thing that I would like to point out during my work in the Houston, this is where I started becoming aware of the importance of digital oil field when I was working for Weatherford. Now, here you are looking at bunch of names and logos. These are the companies that I have worked with over my career. I have taught classes or I have done consulting. Here on the top right, you are seeing some of the universities where I have given my talks. I have taught a semester-long seminars or semester long courses actually or seminars. On the lab side, there are several consulting company, training companies through which I have worked. Bottom line is that I have been fortunate enough that I was able to go around the globe sharing some of my knowledge, whether it was through distinguished lecture series or when companies invite me to teach semester long, not semester long, it's a week long, which translates into semester long curriculum at the university, about 40 hours of instruction. So the guy who had not set a foot on the plane until about 30 years or so managed to cover now 54 countries and quite a few countries multiple times. So I'm extremely grateful and thankful, and all of that goes to the oil industry. Now, enough about me. Let's learn about you. What you can do is you can point your phone at this barcode. It will not steal any of your data, but it will let you join this survey that I have asked, just to so that I can understand who all are attending and what are your what is your background, etc. Okay, so just point your phone at this, and then there'll be two, three questions. I'll not bombard you with a lot of things. There are two, three questions that you will be asked. And what I'm going to do is that I'm going to switch over here to the website. So you can even point here and you can start answering this question. So far, three persons have joined and one person has responded. Uh, I'm trying to understand what is the background of all the people who have joined. Based on the introduction, it seems that um, it is fair to expect that most of you are either senior or master's PhD or industry professionals, including faculty or alumni. So please, the first one I'll give slightly more time so that people can join. Um, and then we will go. And there are some fast finger quizzes also later on. So I think we have about 13 or 14 people or 15 persons, including me. So I'll wait for about 10 people or so to join. So far, about five of you have answered. Thank you for that. And seven have joined. So the ratio is 60-40, master's, PhD, and faculty, alumni. All right. Okay. So I think this tells me roughly most of you are a graduate or industry professionals. Thank you for answering that. Let's go to the next one. Uh, what specific areas have you focused your efforts on? And I'm giving you opportunity to give primary versus secondary. And then there are five possibilities: drilling, production, reservoir, geosciences, data science, AI, ML, and not in the upstream. Now, before getting onto the seminar, I didn't know that IIT Guwahati did not have a petroleum engineering program, and you all are just like me, where how I started. You all are chemical engineering graduates. So, but still, I would like to see what is your primary versus secondary area of focus. Um, looks like production seemed to be the primary focus here. Or you may say not in the upstream, which is it could be chemical engineering. So looks like there is some interest in geosciences and there is some interest in data sciences. Some people have responded not in the upstream. So far, three persons have answered. And by the way, you can also join this from your laptop if that is how you're joining by just going to this website, ahaslides.com/ALS rules. Okay. So it looks like production is about 1.3 out of 3 responses. And then there is a geoscience and reservoir. And then there is some interest in drilling also. I'll give a couple of more answers before we move on. All right. I mean, this gives you an idea about your colleagues and what are their. And by the way, I'm not capturing any names or anything on the back end, so feel free to answer freely, or this is not going to go anywhere other than on the recording, so nobody would be able to identify who has answered what. Okay. All right. The next one is about what would you like to learn from today's webinar? And this is a free form uh, question. And what you will need to answer are some phrases or some words, and you can enter up to three entries here. So I'm expecting to see some kind of word cloud coming up, right? And I appreciate the participation of those who are, and the rest, please do consider joining this. It's just kind of fun and trying to understand because as I see, there are about 14 people and not more than five of you have logged in. Basics, applications, modeling, very good. As I said, you can enter up to three entities. And basics, you shall get it. I understand you have a whole course. As far as the modeling part is concerned, just to set the right expectation, I'll give you very generic because, as I said, artificial lift itself can up to about a semester long, which is a 40 hours curriculum, not to not including the homeworks and assignments, etc. Very good. So digital oil field, modeling, AI applications, data analytics, basics. Yeah, AI applications and data analytics is very, very hot field. Um, and I have some extensive work experience in that, I would say, if I may say so, including virtual flow metering. And right now I'm working on one of the Gen AI applications. Hopefully, it will be ready in another month and half's time frame. That will be aimed at preparing this the modeling aspect, meaning primarily designing and such. So uh, I can see that problems in artificial lift, well digitalization. So it seems that digital is capturing a lot more uh, response. Now, ML in secondary recovery. Now, secondary recovery, the moment you mention that, to me, it means you're talking about reservoir engineering and related applications. And I am not the person for that. I am production through and through production guy. Okay, I do understand enough. And just an interesting tidbit I would like to share. Last week I was in Santa Fe, New Mexico, where we had a 3 day forum on artificial intelligence, what it will be like in upstream oil and gas by 2030. And we had representatives from Reservoir, G&G, drilling, completion, from production, quite a few from the production, etc. So very, very interesting discussion we had. Now I'm moving on to the next slide. And this means I need to go back to the presentation. So thank you for those who participated. And by the way, hang in there with that website. We'll have some quiz coming up later on. So first part is artificial lift, the basics, what, where, why, when, how. W4H. So any topic you pick up, you do W4H and you get lots of background. So conventional reservoir, what you're showing, what you're seeing here on the left side is a production profile over the time period. As the well is put on the production, there is some plateau period or slight decline, and then there's steep decline. And the artificial lift is applied at any of this phase. And typically, conventional oil field artificial lift is applied once the production goes below whatever is the target set up by the business as well as the reservoir consideration. And when you move to unconventional reservoir, which is all the like there's significant excitement here, at least in the United States, to some extent in Argentina as well as Saudi Arabia. What you're seeing is that there is steep decline starting from almost day one. And I have worked with the well where on day 365, you might lose as much as 40% of the production of the day one, right? Or even more. Now, of course, we are using better choke management practices. But the bottom line is that artificial lift in unconventional is applied much earlier. Part of the reason is that people are trying to recover their investment faster. So your takeaway from this slide is that almost all oil and gas producing regions rely on artificial lift. This gray shaded area that I'm showing is where a well is on artificial lift or a field is on artificial lift, right? All oil wells and most gas wells will require artificial lift at some stage. And oil wells rely on artificial lift system for majority of their productivity. So there are some wells I have seen up to 100 years old and still they are working, and they were put on artificial lift maybe in year 5 or 6. It was the case earlier, even in conventional, that you would not put the well on the artificial lift because of the stronger reservoir. But nowadays, most oil companies prefer to go with the artificial lift earlier part of the life cycle. So this is a very useful skill if you're going to work in the production engineering, right? Um, Now, why do you need artificial lift system? Basically, production acceleration, as I mentioned. Infill drilling also brings up artificial lift requirement. EOR strategy changes when you have tired production, meaning a brownfield type of production. Then, as is shown on the right side, pressure decline or the water cut increases. That is where your available energy is not sufficient to produce the quantity that you want. And then the production optimization. And production optimization is a catch-all term for basically production enhancement. But later on, you'll see that it means a lot more than that. Okay, so here is one example from Latin America on the project that we worked on late last century, right? Where many of you were not probably born. And what this study brought forth is that if the well was put on naturally flowing, then this is how the production profile would be over 8,000 days Whereas if you add some gas lift later on at around 4,000 days, then this is how the production profile is. And if you put it on ESP, this is how the production profile is. On the right side is a cumulative production, what are known as cumes. This is a naturally flowing production over the cumes, about 600,000. If you put it on gas lift, then you're recovering almost 700,000. If you're putting on ESP, then your cumes might go as 800,000. Your takeaway should not be that ESP is the way to go and it is better than gas lift. It just so happened for this particular field that ESP was performing better than gas lift. Nowadays, if we had considered the same approach, we might have come up with different conclusions. Your takeaway should be that artificial lift can be helpful in recovering the barrels that would be lost otherwise, and you can also accelerate the production. So when do you need artificial lift? You might already guess the answer. But if we look at a simple basic, there are two boundary conditions, reservoir pressure and the wellhead pressure. And wellhead pressure is kind of determined by your facilities, how far they are and what are your separator, manifold pressure requirement, whereas the reservoir pressure is whatever it is, right? So for a specific flow rate, again, keep in mind specific flow rate and flow conditions, including water cut, gas oil ratio, API gravity, etc. You will have a corresponding bottom hole flowing pressure, which is the pressure at the bottom of the wellbore. And then there are some pressure losses along the wellbore. So you need artificial lift to bring the fluids to the surface when available reservoir energy is low, meaning either fluids are not flowing to the surface or you are desiring higher than the naturally flowing quantity. That is when you think of artificial lift. Now, this is the only expression that I'm going to show. As I said, this is a semester long curriculum, and that's where we can talk more about this. But just for the purpose of the webinar, I'm keeping this discussion at very high level. So why am I showing you this not partial, the differential equation? Basically to give you an idea that pressure differential, the total pressure differential is function of three elements. Elevation losses, meaning you are gaining the height when you're coming from the bottom hole to the surface. In the process, you are losing the pressure because you are working against the gravity. And then there are friction losses. Friction losses always will work against you because you are there is a solid surface against which your flow rates are happening. And then there are acceleration losses. For most part, we ignore basically acceleration losses unless you're working in high pressure gas and that which is flowing through some constriction. But coming back to the elevation and friction, as you can see, elevation is directly dependent on the density of the mixture flowing through it, as well as the inclination with respect to vertical or horizontal, depending upon how you define. In this case, it is horizontal. Okay, and then when it comes to friction, you're looking at the velocity of the flow rate and the diameter primarily. And then there is, of course, there is a friction factor that you also have to look at. So why am I showing you this? Just to make you aware that you have to pay attention to the density, then the velocity or the diameter of the tubing in order to determine what are the friction losses. Okay, so this is the only expression. So your takeaway is that you need artificial lift when available energy is not sufficient. And this next graphic will basically reinforce that point. So again, there are two boundaries, reservoir pressure and wellhead flowing pressure. And then initially, when the reservoir pressure is high enough, you have some losses into the reservoir. And this is the bottom of flowing pressure. And then for a specific flow rate and flow conditions, your well is flowing. Now, what will happen over the time? Your reservoir conditions change, your water cut increases, your pressure drops, and in that case, the flow rate that you are expecting, you are not able to get. In many cases, the well ceases to flow at all, like as is shown here, because this gradient is not reaching for the available wellhead pressure. So in that case, you have to insert into the wellbore something called artificial lift at some depth, and that artificial lift will, that system will introduce what is called total dynamic head or boost. And that boost will allow you to flow to the surface in the desired quantity. That is the function of artificial lift. So we have looked at when side of it, what side of it. Now, let's look at a little bit of modeling aspect. If you have worked with nodal analysis, which I spent a week talking about in Tunisia 2 weeks ago, you know that there is an inflow performance, which is the reservoirs performance, which is a pressure versus the flow rate. And then the green line is the outflow or the tubing performance. Most of the time we use term tubing because the production is through tubing. And when the two of them intersect, that is the stable equilibrium point. Now, this is the flow rate that well would produce under the available reservoir energy and the back pressure exerted by the production system. Now, if you want to produce to the right of this stable equilibrium, that is where you require this boost from artificial lift. Okay, we do not have time to go through the expressions that requires. Now, when your outflow curve does not intersect, that is where you say that, hey, my well is dead, and you have to implement some kind of artificial lift. Or by the same token, if your reservoir pressure declines and reservoir conditions deteriorate, in that case also your production declines and you require artificial lift. Okay. Now the next question is, after looking at what, why, let's look at some of the hows, how we are lifting the liquid. So there are different types of artificial lift systems, and here you're looking at all the major. The first one to the top left is reciprocating rod lift or beam pump or sucker rod pumping or rod lift. Um, and we all are familiar. Actually, this is a symbol of our industry. The second one on the right is a progressing cavity pump, which is primarily used to lift heavy oil or coal bed methane. In India, we are using that for coal bed methane or coal seam gas production also because of, and again, I do not have time to explain all the details, but again, this is a reciprocating and this is the rotating motion as this show. The next one is electrical submersible pumping or ESP, and that is a more familiar centrifugal pumping type of application, except this pump is very slender and lowered inside the valve bore. By the way, all the three, this method that we have seen, they are all pumping methods where the system is lowered inside the valve bore. Next comes the jet and piston pump that doesn't occupy more than 2% of the application worldwide. And what you're looking at is some kind of high pressure fluids going down and driving the pump downhole, whether it's a jet style of pump or piston type of pump. Okay, so what you're looking at is a jet type of pump here. Then coming here, you're looking at the gas lift. Remember earlier we saw in the elevation losses, there is a dependency on the density. So gas lift works on the principle of reducing the density, whereby you're injecting high pressure, low density gas into the production stream, thereby reducing the mixture density and bringing it to the surface. Next comes the plunger lift, where a small solid piece of metal that travels up and down using well's own reservoir energy to deliver little quantity of liquid to the surface. And then finally, this is a foam injection where we are relying on reduction of surface tension of the primarily water type of liquid, even though you can do it with oil, but oil doesn't work that well. So, from the chemical engineering perspective, foam injection is something that we can all very quickly latch onto, whereby you are injecting some surfactant, which causes the foam, which reduces the density as well as decreases the surface tension and bringing in all the liquid that is accumulated at the bottom. We can also relate to gas lift and plunger, as well as all forms of lift method. If we think, we all have taken transport phenomena course, which is Bird Stewart Lightfoot or some other textbook that you might have used. So that part of chemical engineering has served me throughout in the production engineering aspect of. So if you say that, hey, I'm chemical engineer and what, don't lose heart, just focus on the fluid mechanics. Of course there are other principles like control systems theory that also comes handy, but I'm now going off the track. There are other ways to lift the liquid, and you can reduce the wellhead pressure. You can apply some surface boosting. You can put some surface jet pump, surface multiphase pump, or surface compression. You can also increase the downhole gas velocity by reducing the diameter of the flowing string. It is called velocity string or dead string. Okay. You can do hybrid, which I do not typically recommend. And then there are quite a few emerging technologies like downhole compression and downhole multiphase pump. Now, with this, let's look at the classification of the artificial lift methods in terms of the energy source. So on the left side, you're looking at the plunger lift, foam lift, and gas lift. All these three lift methods primarily rely on the reservoir energy. Okay. Primary reliance is reservoir energy. And on the right side, whenever you see any lift method that has a pump in it, they are all pump assisted. What's the difference between two? In pump assisted lift method, you're lowering some mechanism into the wellbore, and that mechanism is energized from the surface, meaning you require energy source at the surface to drive that pump. Whereas on the left side, what you're looking at, the reservoir assisted, meaning primary reliance is on the energy source. Now you can argue with me that, hey, gas lift requires some compression facilities at the surface, and you won't be wrong. My counter argument would be there are some autogenous gas lift also where you can use nearby wells, higher pressure to drive it. But anyway, we are not splitting the hair. Your takeaway should be that plunger foam gas lift relies on reservoir, whereas rod lift, piston pump, progressing cavity pump, jet pump, and ESP, they are all pump driven methods. I require a power source at the surface, as well as I have to intervene inside the well bore by lowering something. Next question comes up, which I can produce. Now, never talk in terms of the producing the oil. We are lifting liquid from the bottom, right? So always talk in terms of how much of liquid production I can get. And as a matter of fact, most of the artificial lift methods worldwide are lifting, majority of them are lifting higher percentage of water, because that is one application of artificial lift, right? So here, plunger and foam lift method, they are typically lower than 100 barrel per day. You can find me a well that might be producing 150 or 200 barrels, but they are kind of outliers in my opinion. Whereas on the other end of the spectrum, you can have jet pump, ESP, gas lift. They can go as high as 30,000 barrels. I have seen some wells producing 30,000 or even higher in some fortunate parts of the world where they have prolific reservoirs, right? And then middle of the road lift methods are typically reciprocating rod lift, progressing cavity pump, and piston pump. And typically they produce less than 1,000 barrel per day. You can stretch the envelope to go up to 1,500. Now, one thing you have to keep in mind that the methods on the right side, they have now capabilities, meaning the vendors or the service companies have developed equipment that can go onto the left of the spectrum. Meaning, I have worked on the ESP wells or the gas lift wells. ESP wells now can go as low as 50 barrels per day. If you had asked me 15 years ago, I would have said 1,500 barrels per day is the lowest limit, right? But nowadays we have the equipment thanks to unconventional. Gas lift wells, I have worked as low as 10 barrels per day and as high as 20,000 barrels per day. The ditto for rod pumping. Most of the rod pumping wells in the world are producing less than 10 barrels per day of liquid, right? But then I have also worked with wells that produce as high as 2 or 3,000 barrels per day. But they are again, as I said earlier, outliers. Now keep in mind that all of these methods on the right may go on the left, but the methods on the left cannot go on the right because there are some physical limitations. For example, if you say that, can we produce with rod lift something more than 2,000 barrel per day? I said, yeah, you have to probably align a lot more stars to do that. It is possible, but it is not doable for most of the wells in the world, right? So now let's go back to our quiz time. And I'm going to bring up the quiz, and I would like you all to join as much as possible. And remember, this quiz, fast fingers get higher points. So we are going to have some fun time here also. So those who answer fast will get more points. And if you have given a name when you join this slides, then your name will show up in the leaderboard. And sometimes people give some funny names also. So I'll give a minute more for everybody, for more people to join. Right now, I see only 4 people have joined. I hope this is joining the internet is not a constraining factor for you. This will be fun, I promise. Okay. So I can see we have about 17 or 16 people on call. Maybe there are not that many bots here. So I would like you guys to and ladies to join. All right. Okay. Wonderful. Somebody has given me already thumbs up. Thank you for that. So ready, set, go. All right. So I'm starting it here. Already 6 of you have joined. Quiz question. There are 3 quiz questions coming up. Which lift type has most installations? And your choices are all 1, 2, 3, 4, 5, 6, 7, 8. Don't overthink this. Go with whatever understanding you have, right? And as I said, these are fast fingers, so I would like you to pump in faster. And again, I'm not recording who answered what, so don't worry. There are no repercussions if you even if you answer wrong. So time is up, and we have only 2 answers. Come on, I said fast fingers. All right, so somebody said ESP, so the correct answer is sucker rod pumping. That lift type has the maximum installations worldwide. Okay, I suppose this is probably late and you guys may be tired, or maybe it is too early if you're joining from here or other parts of the world. So are you ready for the next one? Question number 2. Okay, 4 points for fast answers. Which lift type gets the most capital? We are talking about annual investment in the artificial lift method. And again, you have the same choices. Okay, gas lift, ESP, PCP, rod pumping, plunger lift, hydraulic jet pump, piston pump, and foam injection. All right, we have 5, 6, 7 answers. Come on, 6, 5, 4, 3, 2, 1. We have 7 answers. Thank you. Okay, are you ready to see the answers? All right, the correct answer, whosoever said ESP, the one person said ESP, that is correct. That one gets more than 50% of the capital on annualized basis. Electrical submersible pump. Now, this is the third question coming up. Ready? Let's go. Which 2 lift technologies produce the most oil globally? Now you have to select 2 answers, right? Again, your choices are same 8 choices. I'm keeping it short time because we have lots of ground to cover. So if you feel that I'm rushing you, it's on purpose, right? 2, 1. So 6 people have managed to finish it. And are you ready to see the answers of the 6 people? The correct answer is ESP and gas lift. So whosoever answered that, pat yourselves on the back. All right. And so H2O. Woohoo! He got the 126 point, followed by Mr. Parag. And but anyway, thank you. And no more quizzes, okay? I know it's end of the day, but this was a kind of just a little fun thing I thought I would throw in there. All right, so moving on. Now, earlier I said that artificial lift ESP gets the main, but overall, if you look at the artificial lift's importance, when you compare to the investment in 99 versus 2024, artificial lift got almost 7.5 times in that particular day's dollar. This is not inflation adjusted. As against that, the highest method is pressure pumping, and we all know why pressure pumping gets so much of dollar, primarily driven by the unconventional. But one thing you have to keep in mind: artificial lift market stays always I would say robust. Even in during the downturn, which happens quite frequently in oil and gas industry, artificial lift market is the first one to recover because you have to keep on operating the wells that are already producing. And you have to keep on fixing the things, you have to keep on putting in the new lift systems. So artificial lift is relatively, as you can see here, it's a good market to be in. Now, here is one distribution that was given by Dave Carpenter during his talk in 2016 as to how Shell is lifting the production. And this is primarily conventional production, right? And as you can see, they are producing a lot more using gas lift, followed by ESP. Earlier, beam was much higher in 93. And that also tells you about different type of assets that we may be operating. Here is another picture. This is relatively more recently from ConocoPhillips, given by Bill Hearn. And what this picture is showing, and it's quite detailed, and there are a lot more details, but your takeaway should be that, okay, even though plunger lift is saying that highest number of well count followed by flowing in there, but in terms of barrel oil equivalent per day, they have self-flowing wells. Okay, so in 2022 numbers, gas lift is producing highest amount, followed by ESP, followed by flowing wells, followed by rod pump. Now, this constitution changed over the years. As you can see, 2013, the picture was different, but still gas lift and ESP were two leaders for that. Okay, so this is some interesting stat. Unfortunately, we do not get the stat worldwide. Now you said, okay, enough about artificial lift intro. Tell me what I need to know about artificial lift. So I would say, think of the challenges. What type of asset you are working in, right? Is it a mature or a greenfield or unconventional? That helps you narrow down. Then where it is located, the wells are located onshore, offshore, deep, subsea, hot, cold, wellbore conditions, what are the completion, casing tubing sizes, etc. Very, very important factor, which is the PVT. Okay, do you have too much or too little gas? And what do I mean by too much or too little gas? You're not talking about gas oil ratio measured at the surface condition. What is the actual gas encountered in the wellbore? Because all the pumping methods they hate, they do not hate, they do not like it because the pump, whenever it ingests lots of gas, then it gets deprived of the volumetric efficiency. And in some extreme cases, it can lead to what is called gas locking or cavitation. This is not the time for me to discuss this, but short takeaway, all artificial lift methods except for gas lift, plunger lift, and foam injection. All the other pumping methods do not like gas. Then too much of water, of course, our density goes up, your horsepower requirement goes up. Then heavy oil, the same thing, horsepower requirement as well as the viscosity increases the friction also. Sandy oil, it causes lots of problem, friction, downhole friction, as well as the pumping surfaces do get eroded. And then there are scales, wax, asphaltene, H2S, CO2. This leads to all kinds of what is called flow assurance issues, right? Then the reservoir side of it, there is a lot of uncertainty. We do not know all the time, except it's conventional and brownfield, right? Horizontal completions leads to some challenges. Also, most important, mindset of the people. If you are familiar with one lift method, switching over to another lift method is a big challenge in the oil field, right? Budget is always a constraint, power availability. If you are going to use any pumping method, then you have to have a power nearby, right? And production optimization is another interesting aspect. So here are your takeaways. This is very important slide, right? System selection. You have to keep in mind well is a dynamic entity. It is not a stationary, even though we use all the time steady state expressions, right? And the lift system requirement can occur at any time during the well's life. And then you have to keep in mind that it is not set and forget type of system, meaning you lower one lift and you're done. No, you have to, even for the same lift method, you have to keep on changing the equipment sizes and specifications, or you may altogether go to some other lift type, like as is shown here in the graphic. One example, like it started with the naturally flowing well and then gas lift or ESP, and then toward the end of the life cycle, rod pump or plunger. So you have to always think in terms of the well's life cycle. What is the available energy in terms of reservoir? What is the water cut? And what are the tubing sizes, etc., etc. But the key takeaway, lift systems efficiency and reliability changes over time, and it requires continuous adjustment, right? And here is one graphic that shows conventional life cycle. You typically have one or two types of lift methods. Now, when you go to unconventional, you will see there are plethora of choices. And I'm not going to walk you through. I'm seeing that I'm spending a lot more time than what is allocated here. All right. But your takeaway is that you have to use different lift system that is applicable. So what are the technology application processes? You have to look at the reservoir analysis, wellbore analysis, and nodal analysis is the most important part. These are all the things that I learned after I joined the oil industry for your information. I never learned this, but the principles, some of the engineering principles still apply. Then comes the lift selection and the design aspect, economic analysis, etc. Nowadays, what I'm hearing from the field practitioners is that design is design. Once you lower the design in the well, you're not going to pull it. So you have to focus more on the last item, which is the optimization approaches, right? Which is well site, desktop, or collaboration and analytics, which is a very, very hot area. Here you are looking at a cheat sheet, so to speak, and it has quite a few caveats that all these numbers of maximum depth and maximum volume, they do not jive together. Either you can get maximum depth or you can get maximum volume, not both at the same time, because the horsepower that you can deliver at the bottom of the well bore, you will be constricted. Okay, here are the list of all the commercial software. This may not be incomplete. I should not have used word all. This is not the most comprehensive list, but this gives you an idea about the choices. And another thing that your takeaway is that depending upon the lift method, you might have to switch software. I have my own favorites and such. And I do not want to go into that. But if you are attending my semester long curriculum, then you'll be asked to use one software to solve the different problems. Now let's switch gears and go into unconventional, how the artificial lift has evolved to address unconventional over the last 15 years or so, right? And one example that I'm bringing it is from Permian Basin, but this applies to Eagle Ford or Bakken or any field, any unconventional field elsewhere in Saudi or in Argentina, etc. Okay. So what you are seeing here is that if Permian was a field by itself or a country by itself, it would be number 4 in the world, right? Which is producing roughly the latest number that came out about a couple of weeks ago. It is producing almost 48% of the oil crude production for US. And US is the largest producer right now in the world, about 13.4 to 14 million barrels per day, right? So this gives you the importance of the Permian. By the way, Permian Basin, if you do not know, it's in the northwest corner of Texas, and part of it also covers the New Mexico state, where I was last week. And I'm sitting in the Texas state. Okay, so the key challenges for the shale and tight reservoirs is well depth geometry. Now the laterals are going about 10,000 feet, and now there are horseshoe type of completion. And this type of slender well geometries causes some lots of problem. Like you have downhole separation going on. So you have transient mixed phase, sluggy and turbulent flow happening inside the wellbore, which directly impacts the artificial lift systems. Of course, reservoir has its challenging because of the stimulated reservoir volume, which is ultra low permeability. Your gas oil ratios fluctuate wildly depending upon how natural fractures intersect with the wellbore and how you have fractured it. Then again, all the nasty sand, paraffin, scale corrosion are bigger challenges, and the power supply, right? So, but the takeaway is that unconventional production is highly varying. It varies drastically. I gave initially example that over the year I have seen over the first year the production dropping as much as 60-70%. Nowadays, of course, it doesn't drop that dramatically, but the fact remains that you require an artificial lift system that can handle widely varying production rate over shorter time period. And there are some constraints. So we think along the lines of what is the early production phase, and early is a kind of subjective, and we can have a discussion about that, or the late production. Typically, when you have this asymptotic tail happening, that is the late production time. So in the early production meaning high production rates, right? Relatively less problems and less gas and such. In that case, as we saw earlier, ESP, gas lift, and jet pump are the ones because they can produce higher. Why would foam lift come here? That is for the gas well. Unconventional gas wells, the when you're removing the water quantity, right? Because your primary production there is gas, not the water. Water is just obstruction. So ESP has been a darling of early production because of the acceleration of the production, and you can produce high flow rate. But then the challenge comes when on month 3 or month 4, your production declines, and this is not the class to walk you through the ESP characteristics or catalog codes, etc. But you have to remember that each ESP equipment, they have their recommended operating range. So once the production falls outside the recommended operating range, then there are significant challenges and the equipment may prematurely fail. And that's what has been addressed by ESP vendors who realize that change is a challenge for ESP life cycle. So they have come out with systems that can handle wider operating range, and operators also switch over very fast. There are permanent magnet motors that have come up for energy efficiency and easy installation because they are shorter also. There are improved pump stage geometry as well as the gas handler for high gas content. Again, I typically discuss this over a couple of hours. So I'm kind of giving you very high level brush. Here is a picture case study from ConocoPhillips as to how they are using gas lift and how they are switching from tubing flow to annular flow with high performance gas lift. These are some of the innovations that companies are trying, high performance gas lift, etc. The drivers are reducing compression cost, reducing early life lifting cost by almost 2 barrels oil equivalent, right? And ConocoPhillips is using for lower gas liquid ratio wells that have less than 2000, right? Because they have lots of ESP early life failures they experience. Anyway, again, your takeaway should not be that, hey, go with the gas lift or go with ESP. Your takeaway should be that each lift method has its own applicability and you have to determine on case by case basis. Once you approach this late life production flat tail, then you have to consider maybe gas lift or different forms of gas lift. You have to look at rod lift, some cases piston pump, and plunger lift. Foam lift is again primarily for not only injecting surfactant, but also sometimes you inject corrosion inhibitors, asphaltene or wax inhibitors, etc. So in my experience, I've seen typically people using different variants of the gas lift, plunger lift, of course, in combination with gas lift and rod lift. These are the primary methods. But jet pump could also be used, though it can be highly energy inefficient. Right? ESP definitely no, and PCP is typically not used in unconventional production unless you call heavy oil as unconventional production. Okay. Now here is a case study from Occidental presented way back in 2017 by ex-SPE President Shauna Noonan, who is their production fellow. And Shauna's point was that Oxy had lots of trials and tribulations. And when they started with ESP, there were lots of challenges in the Permian bench. And they finally settled on gas lift progression in such a way that you always start with the annular production, then you go to the tubular production, which what she calls conventional, then you go to intermittent gas lift, then you go to gas assisted plunger lift and chamber lift. And I have seen quite a few other companies' practices, and I have developed this particular graphic. So again, you start with jet pump or ESP. Jet pump is a natural choice because it is also used for fracture fluid recovery. And then you switch to ESP, or you go with high performance gas lift or annular gas lift. Then you switch to tubular gas lift. And then what is called PAGL or continuous plunger assisted gas lift. Then you move to plunger lift, then you move to GAPL or gas assisted plunger lift. And then there are variation in between. You can also go to the rod pump also. So your takeaway is that artificial lift system requirement occurs at any time during all oil and gas wells life cycle. There are a variety of lift system. Never answer that this lift is better than the other. You have to study. Not all the lift applications options will be applicable for each well or even a well type. Even in the same field, different wells may be good candidates for different. And that's why if you go to the operator, you might find that they might be using two or three or four or even more types of lifts. Okay, sometimes it's a science experiment, other times it is actually a necessity, right? Now, different types of lift systems can be applied on a well at a different times, as I have been impressing upon you. Lift systems efficiency and reliability changes over time, which is very, very important. And it will be great segue into the next topic in a minute that we'll go over to. So you require continuous adjustment for an optimum operation, right? Now, going back to the Permian, all operators rely on artificial lift for profitable asset operations, right? ESP gas lift are preferred lift forms during early to mid stage of life cycle for tight wells or shale wells, and high pressure gas lift is also used, whereas gas assisted plunger lift or GAPL is used for mid stage typically, and then rod pumping is used in as well as PAGL, plunger assisted gas lift, and plunger lift are also used for late life cycle. Okay, so your takeaway should be this picture that there are variety of systems and different systems can be applied at different times, and you have to keep an eye on each and every any lift method that you're in. And that brings us to the question of digital oil field for production optimization or production acceleration. All right. So when we talk about digital oil field, the first question comes up why we are going. And that question is answered with one word, which is production optimization. Now, production optimization can be defined differently depending upon your area of focus. Like when the drilling person talks about production optimization, they talk in terms of rate of penetration, etc. Reservoir people have a different view of it. My definition of production optimization is purely related to the operating production professionals only, meaning I talk in terms of what comes out and what it costs me to get it out of the field, right? So on the y-axis, we have revenue. On the x-axis, we have time. So revenue declines because the production declines with the time. On the other hand, the lease operating cost as well as the installation changeover cost keeps on increasing. So when I say cost, it's a kind of combination of both um, capital as well as the operating cost, right? Maintenance cost included there. So whenever the revenues are higher than the cost, you have profit going on. That is a profitability envelope. The moment costs take over the revenue, then the time to plug and abandon that asset. Now, what if you can apply some operating procedures as well as better practices so that your revenues increase a little bit, whereas the cost decline a little bit. All of a sudden, you are seeing your profitability envelope has expanded. And another thing that most of the people miss is that you have pushed your shut-in point to the right, meaning you have recovered the barrels that would have been lost if you had shut in earlier, if you had not applied the production optimization methodologies, right? So the goal of production optimization is to maximize reservoir production, not increase the flow rate short term. Okay, meaning you increase the production over the life cycle. One important component is lowering the mean failure rate of the well, meaning the systems that we are applying on the well, whether it's an artificial lift system or you're looking at the well, the word is, we are talking about the integrity of the well system, right? Lowering the cost is very, very important for production optimization. Again, how do you lower it? By reducing the downtime, by minimizing capex, opex, maximizing human resource potential, and doing more with less. That is the main point, doing more with less. And that is the aspect. And then QHSSE is becoming a top priority also, which is quality, health, safety, security, as well as the environment. I think the second S is sustainability. Okay. So this is not an empty talk. There are lots of articles in the Journal of Petroleum Technology, as well as other industry magazines that I'm showing here, where people are accelerating their journey towards the digital oil field, right? We were talking about this digital oil field. It is nothing new. In last century also, there were some presentations, CERAWIC presentations in 2010, when people were claiming improved like production rate, reduction in OPEX, CAPEX, and overall benefit to the company, right? And then there are some relatively recent like pronouncement from people claiming billions of savings, etc. And some of this could be window washing, but the fact remains that we are reaping the benefits of some of this optimization. And digital oil field is a major, major aspect. But what about the operators who are doing day-to-day operations? There are a variety of questions that comes up. Are my wells running? And there are a bunch of, depending upon your role in the oil field, the questions vary. But all of those questions can be distilled in few bullets, like are my wells delivering? Equipment's delivering? Are there any problems that I need to address proactively or plan for? um, are there any failures that I need to worry about? Are there any lease operating costs that I need to focus on? Are we meeting production forecasts? So on and on. The main question is that am I able to put all these practices on a sustaining basis, whatever operating practices that gives me a better return on my investment? And that is where digital oilfield steps in, because that helps you address and solve some of these optimization challenges. But what is digital oil field and where does it fall? And I'm trying to explain this in just one slide. So what you're looking at on the right, bottom right, is the oil field typically scenario. And it all starts with the sensing. And what you're sensing, you're sensing pressure, temperature, differential, load, position, torque, speed, lots of parameters. Whatever you can measure that gives you an idea about the health of a well or an associated production facility, right? That is a key. The sensing part is number one. Without that, you cannot do digital oil field. Then comes the communication. You have to bring all of that sense data back to some center where people can analyze, people can look at it, people can review it. On the other hand, you also require some sort of control mechanism. There is some compute part of it. What do we mean by control? If all of a sudden we sense that some pressures are going abnormally high, then you have to shut it down or you have to take an appropriate action to relieve that pressure. Otherwise, we might have an environmental event. On the other hand, if you're seeing that the well's production is declining and then you need to speed up some pump somewhere, then this control aspects allows you to do that. This communication layer that you put on top of the sensors allows you to watch these things not only remotely but store all of that data, perform some additional computations, and then there are a variety of stakeholders. You can look at it. There are some subject matter experts like ourselves, or there could be some data science, data analyst, there could be some IT persons, and then there are people who are really holding the key to the money bags, right? The people who really care about the profitability of the asset. So all of these people typically look at what is happening in the field by not only what sensors are measuring, but what is computed based on the sensor, right? And that is a key message here. So this slide tells you all that you require sensing framework, you require communication and control so that you can monitor and control the field equipment. You require some storage, data storage, etc. And then you require some analytics. And that is what people get very, very excited about data analytics, what you can do with the data. And this is nothing new. I mean, we have been doing the analytics even when we did not have all the digitized operation. But at that time, we were doing it in not real time or not near real time. We were doing it after the fact, right? But there are several things you have to think about. Data pre-processing. Is my data good enough? Validation, cleaning. And then there are, of course, machine learning aspects of it. And then comes also modeling. You have to have, some people call it digital twins, or basically you can say that you require a well model, you require some subsurface model, you require some network model that says how the field is laid out and how different pressure and flow rate entities interact as different wells join the network, right? And then there is, of course, a production plant. And what do we mean by plant? Separation facilities, compression facilities, water disposal facilities, etc. So there are software available for optimizing the lift methods, and they are primarily based on the nodal analysis. And I showed you some commercial design software that design, when you invert on its head, it becomes analysis, right? In case of design, when you're doing design, you're trying to figure out what system should be lowered. In case of analysis, you already lowered the system. Now, what parametric changes I need to make? And basically, you have two or three possibilities. Either you can change the speed of pump, or you can change the injection rate, or you can change the choke, surface injection choke, etc. Right? And then, of course, you have to integrate for in order to collaborate with other disciplines. There are significant amount of investment being made throughout the world on the service companies as well as the operator side to figure out this data driven approaches. And in the last few years with the generative AI, what is commonly referred to as copilot or GPT, etc., which are large language model based approaches, these things are becoming easier and faster. You can develop the visualization dashboards in no time once you learn how to prompt the system. And then decision aspect requires collaborative environment. So this framework requires some OT, what is called operations technology, as well as the IT, which is increasingly not only information but also integration technologies, right? So it requires support from all of these people. But you remain in the center, you meaning the subject matter expert. So digital oil field progression starts again like this: surveillance, monitoring, and diagnostics, where you lower, and then you go into analysis, then you go into optimization, and then you go into innovative remote control aspect. Okay. Oh, I have two slides. Sorry about that. So on the surveillance and monitoring side, again, as I said, you require sensors, some connectivity, and visualization. On the analytics side, you start with the smart alarms or guided workflows, and then you move over to the real-time control where you adjust the production at the well site remotely, or you do some predictive and preventative maintenance. We'll see some examples of that, and then collaboration groups, right? What type of data do you require? These are the data types you require, and I'm not going to read each of them, but consider this as a cheat sheet. Now, not all of this real-time data is always available. So you have to adjust your optimization strategy, your algorithms based on what data is available. And then some of the other data you may have to use some what is called physics-based model, or you have to infer them, right? And then there are data sets which are not changing in real time, which are your installation data, your PVT data, your well activities. When somebody changed something, what did they change? How did they change? Equipment changeovers, which pump size was lowered, which pump size was pulled out, how we changed the injection rate, etc., etc. But basically, most of the data that I mentioned here, they are not changing that fast, but they are very, very important and integral to the modeling framework. Now, here I'm showing you quite a few real-time trends. The one on the gas lift, the one on the ESP, the one on the plunger, one on the rod pumping. And again, this is not class for me to point out what is being measured and what is being observed and what is being inferred. Your takeaway should be that for each lift method, there are different parameters that we need to sense, we need to pay attention to, and we need to develop some algorithms to handle that. Okay. Um, all right. Good things to remember. Data is not what always what it seems. There are some quality and quantity issues. Some older field infrastructure, you may not have possibility to get even the data out of it. Sometimes your measurements may be incorrect, like downstream pressure may be higher than the upstream pressure. Your measurements may be missing. You may not have, because of the loss of signal, you may not have data available for all the timing. You may have some malfunctioning devices, and then of course people are also fallible in recording some wrong data. Here on the left side, what you're looking at is the spaghetti. Over the time, people start developing the system and with a different mindset, and then they end up having multiple versions of the same data. So lately, companies have started putting in efforts to have a common data integration, meaning there is what is called a one source of the truth and not multiple sources. And that is a key, especially when you're working with your reservoir, for example, reservoir colleagues, and they say that no pressure is X, but your sources say pressure is Y, for example. And I'm giving you very simple. And by the way, these may appear in hindsight or while we are talking about it, this may appear that these are kind of common sense thing, right? But it is not as, I mean, these problems are a lot more common than what one would think. So this is one big challenge, data management, right? Here I'm showing you some very interesting downhole measurements and how people are using it. This example is from Canada, where they are using what is called steam-assisted gravity drainage to use, and they are using fiber optics based measurement system to sense the temperature. And the whole idea is that you are melting the bitumen by injecting supersaturated, very, very high temperature, 250 degrees Celsius temperature steam, sorry, to melt this bitumen and then produce it using ESP. So that ESP where my cursor is hovering right now, right? And the key is maintaining this temperature differential for optimum production. And that's where this fiber optic based system, because the gauges would fail at this high temperature, 250 degrees Celsius. Here is another example that I had a chance to bit review on Gulf of Mexico. It's a gas lift well. And what you're seeing is the temperature and the pressure sensors in these gas lifted wells. And as the we were reviewing the water zone and the water encroachment as well as the gas cap production. And right now, I do not have whole most of time to explain, but your takeaway is that using this pressure and temperature signal, we can get in real time fairly good idea about what is happening downhole and take some remedial measures if required. In this particular case, we were trying to see whether the stimulation actions uh, were effective or not. Here is an example that we published a paper on way back on Permian gas lift shale wells. And again, there are a bunch of measurements happening downhole, which measures the casing, tubing pressure, temperature at multiple locations. And I can regale you with all the anecdotes about what we observed and such. But the main key thing was not just observing these sensors, but then we came up with this algorithm to infer the static bottom hole pressure and the productivity index. These are the two very important factors. And if you work with unconventional data, you see that it's a highly variable and it changes very fast, meaning you require an algorithm that will give you the static reservoir pressure of this simulated reservoir volume very fast by combining the measurement from the outlet of the well and the downhole gauge data. So again, the basis was nodal analysis. So if you have not learned nodal analysis, please do that. Another thing now, everybody gets excited the moment you start talking about analytics, AI, ML. So as this little graphic says, who loves AI? Everybody raises hand. Who wants to learn AI? It used to be the case where most of the people say, it's hard work. And then who is ready to learn Python? And then the room empties. Fortunately, as I said a few minutes ago, with generative AI, lots of these things have become very easy. So do spend some time if you get an idea. I'm now going to talk quickly about some of the examples, what people have done. Like here, this is one of the hottest application, failure detection and prediction using machine learning approaches for ESP. And again, there are a bunch of different researchers that keep on working on this. One is from Weatherford and PDO, another one is from Baker, and this one is from, I think, Schlumberger. Okay. But this gives you a bird's eye view of the importance of this problem and what type of data is required. Here is another example of people working on the rod lift maintenance problem, basically failure analysis and what is happening downhole by using machine learning methods to classify the system. Now, one key thing to keep in mind, even though as developers or as practitioners, we get excited about this machine learning or AI aspect of it, but keep in mind, it's a very, very small part of the entire system, meaning you have to work with lots of other people, IT and OT people that I was mentioning earlier, because you have to pay attention to your data pipes, where from the data is coming, which types of libraries are available or not, how you're going to extract the features. This is, by the way, paper like from Google long, long time ago. And since then, I have had a chance to think about it. I have worked with some AI companies, and one thing I have always come back with impressed that okay, data is data. You have lots of other work that needs to be done. Most of the time, we jump onto the analysis tool, we jump onto the machine learning code without paying attention to when you deploy this solution how the data pipes would be laid, whether you will have necessary access at the point where you are performing the analysis or not. And those things have led to the project failures oftentimes. And when we pay attention to those in the beginning, that leads to typical success, right? Here are some of the GPT highlights about how companies are doing. And these are a couple of years older. And since then, the pace has just accelerated, meaning there are more and more example coming, and if you refer to one petro you will find many many examples of this is happening, right? The key technologies that one has to pay attention, as I said earlier, LLM is one thing, edge computing is another thing, vision is still kind of evolving, I would say. I have not seen very many applications, but then I have not seen a lot of things also. But the bottom line is that companies continue to create AI, ML based solutions and the practices that leads to some significant savings. So, what is your conclusion recommendation? Digital oil field or digital transformation enables the production data capture. So, you have to think in which way you, as a practitioner, will contribute to ensuring sufficient and high quality data. Either you are data generator, data custodian, or a data consumer. Always pay attention to the data. If you short circuit this step, you are going to have lots of gotchas down the road, right? Recipe for making use of real-time data set: infuse the real-time data stream with legacy offline physics-based approaches. This is, you might have heard terminology PINN, physics informed neural network. That is what this falls in. But there are varieties of ways you can do these things, right? Production teams needs to understand and embrace emerging data science paradigms. This is not an option anymore. Do not shy away from cloud computing, edge computing, Python, neural network, LLM. And now here is the beauty. You can use LLM to learn this concept. Actually, I am doing that. And if I can do it, so can anyone, right? So you learn to use, and just don't use these tools in chat windows, right? Read about what are agents, learn to use the agents, learn to use different programming IDEs like VS Code. That is one of my favorite. You can also use Cloud Code. But when you start learning some of this, initial effort would appear to be tremendous. But trust me, once you will get the hang of it, you will be amazed at what you can do. Once you start using LLMs, once you start using agents, solving most all problems are within your reach. And I'm not exaggerating. It's just your creativity, your imagination, and your conceptual idea about the problem space. That is what is hindering most of the people nowadays, in my opinion. Okay. So I wish you very well in this journey if you decide. But it all starts with the fundamentals, like what we discuss in whatever 60, 70 slides that I presented so far, right? So with that, I think we have about 10 minutes at most or so. So we can take some questions. Feel free to uh, turn on your video feed so that I can see, or if you don't, that's fine. But we are open for questions, please. Who's first? Was I that clear that nobody has any question, or it was all whoosh over the head, huh?
Hello.
I know
Rajan,
the name. Yes,
can you hear me? This is Rahul Bali.
of
Uh,
course. I do remember you very well. Thank you for your service.
so nice of you, Rajan. I was just listening to your, when you said that you were at IOGPT with Dr. Ramashish Ray. So I just spoke to one of my, see, I'm the past chairperson of SP New Delhi section currently. And
Yes.
as IIT Guwahati, we have sponsored that student chapter. So
Hmm.
I generally, make it a point to attend their webinars. And one of my fellow
Wonderful.
directors who was with ONGC since 1980, I was just speaking to
That,
him and he said that he also remembers you while you were at IOGPT in 89.
yeah.
So he was with Mr. A.S. Soni, who was the director then, I believe.
Yep.
So very nice to hear that. And thank you so very much for your talk. More
Thank
than,
you.
it is the students who might have gained uh, the entire knowledge from you. So,
I appreciate
and
that
it was very
kind
nice
word.
meeting you and
And
you were the SPDL. I remember when I was on the DL
yes,
selection committee. So
yep, we have worked
thank you so
together
very much.
on quite a few conferences too.
Yeah,
I
yeah,
remember.
yeah. Yes, yes, yes. And so nice of you to have spare
Thank you.
time to talk to the students. And for a short while, even Dr. Sushma Bhan joined the webinar, who is the director DSCA. But she also has a webinar, I think, starting in another 5 or 10 minutes. The
Okay.
director's team talk. So she had to leave.
Okay.
Thank you so very much, Rajan.
Wonderful. No, so here is my one thing. I'm extremely grateful for all my mentors, whether at ONGC or at University of Tulsa or at IIT Kanpur, and most all of them have impressed one thing on me, which is continue to share. And this is my open, I should say, promise, so to speak, that if you guys would like to conduct some more details, even we can hold a workshop. I cannot, of course, travel to if I'm in India and if I'm nearby Assam, I would be happy to come and give in person, but we can always organize some short series of seminars if that helps you, right? Because I often do that for University of Southern California and few others. So why not for IIT? So I don't see any other question coming in. Let me check in the chat box. Do we have anything?
Hey,
No, don't
Rajan.
see any. Yes, Farooq, please go
Rajan,
ahead.
if no one is asking a question, I have one actually. As
Okay.
you yeah, as you move from early production to the late production and you change your techniques in there, say from PCP to ESP to gas lift, etc. How difficult, how expensive it is, and how difficult is it to move from one thing to the other during the life
It's
of?
it's it's yeah, it's a very good question actually, and that this particular question must and need to be assessed before you decide to switch over. Now you have to go into the rationale behind the switchover. People just do not switch over because they like one method over the other method. They switch over because the current setup does not serve their purpose anymore. Either the system has failed, right? The majority of the cost relates to pulling the installation. And what do I mean by pulling the installation? Meaning whatever is lowered in the hole, 5,000, 10,000 feet below, and sometime below the 10,000 feet water depth. The cost to pull that out of the hole is significant. Then comes the cost of lowering the new equipment. Then also you have to take into account the cost of surface setup. Like for example, if you're trying to switch from ESP to gas lift, then you have to think of compression infrastructure. Is it available at the surface? And then the gas lift itself is not very expensive method in terms of the downhole equipment, but you still have to pull the tubing, which can be not as costly if you are working in onshore well, which is 5,000 feet deep. But if you're working in the subsea well, as I said, I'm working with some asset which are about 300-400 meter water deep, then all of a sudden you are looking at $1 million pulling bill, which can be substantial. So you have to always look at the cost of the equipment, cost of the changeover, and then you have to look at the potential production gain. Sometimes your hand is forced in case if the equipment has failed, then you might decide to just go with a different size of the equipment and keep the same lift method. In that case, you do not have to worry about the surface equipment changeovers, right? So I hope that answers your question, Farooq.
Yeah, thanks, Rajan.
Thank you. Okay, there is something in the chat. Which of the artificial lift method can be used for a well facing gas hydrate issue? Okay, so now you have to gas hydrate is a very specific situation. You encounter that typically in offshore or subsea environment. Okay, so hydrates are formed whenever you have your phase envelope, or rather your pressure temperature conditions are in the part of the phase envelope where the hydrate formation is possible. So most of the time, the question to be used is not which lift method to be used. Lift method selection would depend on lots of other things, but typically gas lift is one method that does not get impeded by the hydrate formation, right? Because there is nothing in the wellbore. You are just injecting gas and the whole thing fluid. So first thing first, you have to think of the mitigation of the hydrates. What type of chemicals you are going to add? Methanol is one of the common choices, and there are many other choices, right? So that will shift your phase equilibria so that at least in the downhole or in the wellbore, you will not have hydrate formation. Typically, the rod lift is never used in offshore or subsea type of installation, so you do not have to worry about that. Otherwise, rod may get a problem. But the short answer to your question, ESP can also be used. Again, you do not have anything in the wellbore other than, and typically at the depths where ESP operate, pressure temperature conditions are such that you do not have hydrate formation challenges. Hydrate formation challenges occur closer to the surface or on the surface, right? I hope that answers your question. Thank you, Parag. Sumit Kumar, how does unconventional IPR complicate the artificial lift design compared to? Very good question. And when we were not knowing this properly, we really had big challenges. So I'll take you back around 2008, 10, 12, 14 timeframe. I was working for Weatherford at the time. And Weatherford, as you know, we were kind of numero uno at the time in artificial lift. And what we saw, we did not have ESP, but we had some kind of collaboration. So what we saw is that people are facing a lot of ESP failures. And then we started looking into the well data and we realized that people were pulling too hard. And what do I mean by pulling too hard? Meaning they were basically running ESP to the max so that they can recover the oil faster. But in the process, what was happening was that their stimulated reservoir volume was collapsing. And what do I mean by that? Basically, you are closing the fractures, or you're generating a lot more gas because you're pulling very hard on the valve, meaning the bottom hole pressure is so low that there is lots of gas coming out. So, long story short, what we notice is that the reservoir productivity was declining rapidly. And one of the SPE paper that I showed in the presentation, that was the idea. We were trying to assess how the static bottom hole pressure and productivity index are changing over the time period using the downhole gauges, right? And going back to your specific question, this unconventional IPR, the uncertainty where the things change within the period of weeks and months. Like what used to happen in conventional, that your IPR would change very slowly depending upon your reservoir management practices. The IPR would change very slowly over the time period of months or years at times, right? Meaning your artificial lift system is guaranteed the availability of intake pressure and productivity for longer duration time. In unconventional, because your reservoir pressure, your available bottom hole flowing pressure, and the fluid constitution changing so drastically that your artificial lift system often starts seeing things falling outside the operating range. Because keep in mind, we are talking about a specific set of equipment within the artificial lift system. So, for example, if you have determined that, okay, this particular well is capable of producing 3,000 barrels per day of liquid, right? In unconventional, let's say it's a Permian well. So you sized your ESP so that it can handle anywhere from 2,000 to 5,000 barrels. Typically, people tend to overestimate. Always they push for the higher side to capture the upside. So you have lowered 3,000 barrels, you're producing, you're happy. Within a month's time frame, all of a sudden, your estimate of reservoir productivity were not correct. Maybe there is not enough natural fracture support, or maybe there is some offset fracture that takes away the production from your SRV. In that case, all of a sudden, your well is able to produce only 1,000 barrels. And now your ESP is struggling because it is performing very fine between 2000 and 5000, for example. So the moment you go into 1000, it goes into what is called severe down thrust region. And that is where the pump may start stalling or get gas locked or cavitation, etc., etc. So the short answer to Sumit Kumar's question is that unconventional IPR requires you to basically stay on your feet all the time, meaning keep an eye on the downhole parameters so that you can judiciously make decision. And I'm now scrolling backward to just bring home that point. I have one slide here. You might have seen that slide here. Sorry about if this gives you some little bit of, this is the slide. So if you look into the conventional, you might have just one or two lift methods, whereas in unconventional, very short time period, you are forced to switch over. And all lift methods suffer because of this unconventional IPR. I hope that answers your question. Feel free to have a follow-up.
Since you said switching over to another artificial lift method is costly affair, so
Yes.
in
So,
unconventional
Mhm.
case, so how to count this uncertainty into model so that we model the artificial lift design in such a way that the uncertainty is still is captured itself in the design and giving you the robust techno and economic aspects of the design. So do you
yes.
have any reference
So,
paper on it or something?
there are papers. I mean, if you go into One Petro, there are, and I had written one paper in the earlier part in 2012, 13 or 14, right? Basically to address the same thing. So the idea is, and there are multiple ways. You pointed out correctly, and so did Farooq earlier, that the switchover cost can be a big consideration. And if the productivity changes so fast, or IPR changes so fast and systems fall out, so what do you do? So what do people do? They said that if I have started with ESP, then I will go with the ESP that has a wider operating range. And that's what I was showing here, right? So for example, typically is let's say from 1000 to 3000. In this case, this one has a very wide operating range, 500 to 2500. Now, you see in the bottom part here, this is another pump, and I do not have enough time to describe all the details, but people meaning the service companies have developed the system that can go very, very low, meaning the same pump you can start producing at 600 barrel and then you can go all the way up to 50 barrels. Or another pump, you can start producing at 2500 and go to all the way to 500. Now, 2500 to 500 progression may take up to a year, for example, or even more. Now, with a better choke management and better reservoir management and understanding of some of the reservoir dynamics, SRV dynamics, we are able to run the systems longer. Now, I'm talking about ESP, right? See, here is another example whereby the ESP can go all the way from 200 to 1400. And by the way, there are even more versatile pumps. But then what companies are doing, like if you're using gas lift, then as I showed in the ConocoPhillips case, that they start with the annular flow when the flow rates are higher. And then they have some quadrants or they have some regions that they determine that the moment we are crossing over onto the other side where our bottom hole flowing pressure start declining and the production start declining, then I'll switch over to tubing flow. Okay. And when even if it goes beyond that, then as we saw in the case of Occidental, they started with annular, then they go to the tubular, then they go to intermittent. Now, why Oxy goes this route? Because they said that once we have invested in the surface infrastructure, these are all the downhole changes, which are relatively not as expensive. Plus, we do not have to keep on retraining our manpower. That's another big cost also when you switch the lift method, right? Actually, at one point in Permian Basin, we did not have enough people who understood gas lift. And then the companies figured out that gas lifts operating costs are lower because of the switchover costs are lower, right? And now, then they started moving their people from overseas where they are producing gas lift, or as well as from the Gulf of Mexico where there's a lot of gas lift. They moved all of those people to Permian Basin assets to do that. Hopefully, that addresses your question.
Yeah, thank you.
Thank you.
Whenever you are in Guwahati or would like to visit Northeast, drop a mail to SPE email or personally to me. I will be happy to host you.
Oh, it will be my honor. Actually, visiting Assam is on my bucket list during my next trip to India. So who knows? I might show up there. I mean, the closest to Guwahati I was there. I was in Dibrugarh and Shivsagar area when I was working for ONGC in last century. Uh, but definitely, I'll take you up on that. I would love to do that.
Thank you.
Thank you. Any
Priyanshu.
other question? Yes, please go ahead.
Yes, sir. Any other questions if anyone wants to ask? Right. Right, I think nobody wants to ask. So we'll be stopping here, sir. So as we come to the end of this session, I would like our sincere gratitude to Dr. Rajan Chokshi for taking the time to share his valuable insight and experience with us. We are truly grateful for your contribution to this session and for inspiring. Sir, the recording of this we will share to all the other students who have not joined this also. So is that
Sure.
okay with you?
Oh, absolutely,
Okay, so
yes. Yeah, and if
so
you
I would.
want, Abigail will send you the copy of the slides. Okay.
Okay, okay, sir. And also, I would like to thank for all who has joined today in making these sessions a success through your active participation. A special thanks to IIT Guwahati SPE student chapter for their effort and making this event possible. With this, we conclude today's session. Thank you for all.
Thank you all. Have a good day. Bye
Thank
bye.
you, sir. Okay.